Dr. Rajarajan Sivaraj is principal technical architect at Mavenir, where he is responsible for the standards and the production of the O-RAN architected RIC components and interfaces. His work focuses on disaggregating the radio access network, optimizing the run using SDN NFV principles, and facilitating this end-to-end intelligence in cellular networks using edge cloud. He is also proficient in characterizing and evaluating the performance of various next-generation mobile streaming applications over cellular networks, and that include, these very interesting topics of immersive services, augmented reality, virtual reality, 360-degree videos. Dr. Sivaraj completed his PhD in computer science from the University of California at Davis in 2016, where he studied problems in the area of cellular radio access network design, optimization, and he has actually published lots of interesting research work in different peer-reviewed conferences and journals. He has also many granted and pending patents. He has received best paper nominations for his research work and has been in the editorial, peer review, and TPC committee for many, many international conferences and journals. As I said earlier, really, I'm so proud of what he has done in the last decade. It's really amazing. Today is the opportunity to speak to one of the experts of Open RAN. Rajarajan actually has experience. Now he's working for Mavenir, but he has experience working for different companies, operators such as AT&T Labs Research, Microsoft Research, Intel Labs, NEC, xran.org, Broadcom. So basically, he has ideas about different, players in this ecosystem of telecom as well as even IT. So now, Rajarajan, the floor is yours.
Thank you so much, Professor Tariq. It is a pleasure to be giving a talk here. As Professor Tariq mentioned, Professor Tariq was instrumental in my career in telecommunication networks, because 11 years back, when I was still a kid, in some sense, in this world of research, it was Dr. Tariq's guidance that basically helped me pursue this career in telecommunications. So he was he was a mentor of sorts. He was someone who was extremely instrumental in shaping up my knowledge in telecommunications, because back then I started doing some research with 3G, and Professor Tariq, having been an expert in 3G back then, mentored me towards getting a very solid telecommunications background. I learned a lot from him. It was a wonderful experience when he mentored me in France. I still want to continue being mentored by him and continue collaborating with him. And I'm sure that every day I interact with him, I can learn something very new, and I can definitely keep learning from him in the process. And as he rightly said, the emotion is very true when he said that it was like a father seeing a son grow and achieve laurels. I find likewise. I always feel proud when I achieve something, and when Professor Tariq gives me an appreciation for that. It is an appreciation coming from your mentor and a father figure of some form. So it's a very emotional and a personal moment for me to be giving a talk here, and also share my experience in the space of 5G and Open RAN, which is a new framework which has been revolutionizing the cellular network industry of late, but there is still a lot of work to do. I understand that
Rajarajan, it's a great pleasure to collaborate with you, but
sure.
This time it's my time to learn from you.
Okay.
All right. Okay, go ahead.
That's very nice. That's very nice of you, Professor Tariq. Thank you so much on that note. So the title of my talk today is Open RAN assisted end-to-end analytics in 5G cellular networks. But as Professor Tariq mentioned, we will also be exploring at beyond 5G systems as well. So even though the focus of this talk is on RAN, I want to make it very clear that I do understand that the focus of the group at large is not just the RAN side, but also the core networking side and also the application side. So I've tried to connect the dots across these three components and how you would be able to interface some of the learnings from Open RAN, not just with RAN optimization, but also with packet core as well as application optimization. So it's more of an end-to-end performance optimization that we are going to focus on. Nevertheless, this is centered on Open RAN, but let me try to make clear that this should not be that RAN heavy. We wouldn't be going into all the nitty-gritty details of the RAN. We will try to have enough introduction about the RAN and try to transcend this topic to the core as well as the application layers. So with that, introduction about the outline of this talk, let me first move to the network functions and the 5G network architecture in general. 5G network architecture, network functions, and analytics in general. So there are three key functions of a cellular mobile network across the RAN and packet core network components. One is the control plane that is responsible for connectivity, mobility, UE's context establishment, authentication, and general signaling between the user and the network. This is very much responsible for maintaining the connectivity of the user with the network and typically to manage the user's sessions with the network. And by control plane, we just not mean the control plane of the RAN side, but the control plane of the entire network. The user plane is responsible for transmission of data between the user and the mobile network. And management plane is responsible for configuration of network elements. So your user plane is mainly for downlink or uplink, or offline there is this discussion on V2X and sidelink. So most of the data transmissions between the user and the network is what user plane handles. And management plane is responsible for configuring certain parameters of the network elements. Now this can include configuring the network elements in the core side, configuring the network elements in the RAN side, etc. Now, we will look at some of these functions in detail, but let's basically start with an understanding of the 5G network architecture and see these three components in place. Where do you have the control plane? Where do you have the user plane? And where do you have the management plane? So what you see here is the user equipment, and we just have some high-level boxes to begin with so that we understand things in perspective. So there is the next generation RAN called the 5G RAN, which you're basically seeing here. It has a 5G G node B that's called the next generation node B, or the next generation, that's basically your 5G base station. And then you have, after that, you're basically having two boxes. One is the 5G core control plane, and the other one is called the 5G core user plane. Both these can together be part of the 5G core network. And then the other box, what you're having is the management plane. This is mainly for management and orchestration. We'll be looking at what this management plane is, but essentially, we'll basically be looking into operations, administration, and maintenance whenever we come to management plane. This is mainly for configurations, some some configurations of key parameters. There are also configurations that are done, by the way, in the RAN as well as in the core network, but we'll be able to look at the differences between what kind of configurations are exercised by the management plane and what kind of configurations are exercised by your control and user plane. So this is your RAN architecture. So don't get intimidated by this diagram. I'll try to simplify things in perspective, but this is your 5G radio access network architecture. And this reflects the notion of disaggregated RAN. So 5G has been pursuing something called disaggregating the RAN, which means up until 4G, you had a monolithic base station that had one baseband unit and radio units. And then there came this cloud RAN deployment, where you basically had one baseband unit in a centralized location, in a centralized data pool, that would basically be interfacing with multiple remote radio heads using front haul interfaces. Now that got evolved into this notion called disaggregated RAN, where even the baseband is split into multiple nodes. It's split into multiple nodes. And with the services-based architecture of 5G, we are basically saying that the 5G base station is split into, the 5G baseband unit is basically split into multiple functions, multiple node functions. And these node functions are what you're basically seeing in this box called NG-RAN or 5G Node B. So what you're seeing here is a centralized unit in yellow, which basically talks to a distributed unit in green, which then talks basically to radio units, which is on the far left here. So the centralized unit is in turn split into a centralized unit control plane and centralized unit user plane. So let's try to look this into perspective. So the centralized unit is mainly responsible for the RRC, SDAP, and PDCP layers of the RAN protocol stack. We will look at them in a bit from now. But RRC is mainly responsible for connectivity, mobility, or you must have heard of the RRC signaling between the RAN and the user, which is critical to establishing and maintaining the connectivity between the user and the RAN network. Okay, and the SDAP and user plane, the SDAP and the PDCP layers are responsible for initiating the data transmission. So what you're actually having here is a centralized unit, which consists of the RRC, SDAP, and PDCP layers. And the operations of the centralized unit are mostly in the range, ranging from 10 milliseconds to the order of units of seconds. Okay. Mostly ranging from 10 milliseconds to the order of units of seconds. And mostly these are connectivity, mobility operations, and also trying to maintain the barrier. So always between the user and the network, you establish something called barrier, which is meant to transmit the flows subscribed by the user through the network to the user equipment. So all of this barrier management, we'll be looking at barrier management in a bit from now, but all of these barrier management functions are part of the centralized unit user plane. Okay, and both these operations together are ranging the granularity from 10 milliseconds to units of seconds. The distributed unit is where you actually have the RLC layer, MAC layer, and upper PHY. Okay, physical layer, upper physical layer. Now, these the granularity of these operations range from units of milliseconds to a few tens of milliseconds, mostly units of milliseconds. For example, if some of you have heard about the MAC layer is responsible for resource allocation and scheduling, which means the MAC layer should have to act in the order of units of milliseconds, units of transmission time intervals. In every transmission time interval, which is typically in the range of 1 millisecond in LTE, and it is in the range of hundreds of microseconds to units of milliseconds in 5G because of the flexible nature of the 5G RAN. The MAC layer basically tries to allocate resources to the user on a millisecond level basis. So this is what is the distinct characteristics of the DU. So the operations of the DU nodes are typically ranging from 1 millisecond to 10 milliseconds. So these two have two different granularities. Perhaps one of the reasons why you're basically envisioning this kind of a split disaggregated architecture, where you have a separate centralized unit and a separate distributed unit. Now, the centralized unit and distributed unit, they talk to each other using this F1 interface. This is mainly for interfacing between the RRC, SDAP, PDCP layers of the RAN with the RLC, MAC, and upper physical layers of the RAN. And the DU is then connected to the RUs using front hall interfaces. And RU is responsible for the lower physical layer, which is RF transmission, antenna transmission, and mostly transmission operations, mostly transmission and some MIMO beamforming operations, especially analog MIMO beamforming operations. They are vested with the radio units. Now, as far as the core network is concerned, right? So you're basically having a bunch of core network components, which I guess this group is particularly pretty familiar about. A bunch of these core network functions are part of the 5G core control plane, mostly responsible, whenever you talk about control plane, it is mostly responsible for connectivity and mobility, and also allocation of sessions to the users. Say, for example, the AMF is one function that is mainly responsible for access and mobility management for the user. Similarly, your session management function, SMF, is one more component that is responsible for the user's sessions. Sessions are nothing but traffic flows, IP traffic flows, between the user and the application. And then when you have the what you next have is the 5G core user plane. This is the user plane function that is responsible for transmitting the data to the G node B, which further transmits data over the air to the user equipment. Now, the user plane function interfaces with the data network so that they'll be able to get data from the application server, that is the remote application server that is on the other side of the data network, and would transmit this to the radio network and for further transmission to the user. The user plane function also, in some sense, interfaces with the control plane function of the core network. Then you have this management plane function. What you're seeing here in this slide are two components, which is the MDAF and the NWDAF. The MDAF is in the management plane, and the NWDAF is in the core network control plane. Now, this MDAF is what is called as management data analytics function, and the NWDAF is called network data analytics function. Now, the reason why I have circled these two functions is because these are dedicated for analytics. While up until LTE, right, most of the most of the components like S gateway, P gateway, MME, and components on the RAN side, there was not really a dedicated function for analytics. With the advent of the M plane, or with focus coming on the M plane, people started to look at M plane as more of an analytics component. And with 5G, you have dedicated 3GPP defined functions meant for analytics. One is the NWDAF, that is what we have on the core network, and the other is called the MDAF, which is basically in the management plane of the 5G network. So let's look at these components in detail to understand the perspectives for analytics. Next slide, please. Yeah, yes. So what is the need for analytics in a 5G system? So your the procedures what you have in a traditional network are not necessarily optimal. They are neither data-driven nor programmable. These are typically vendor proprietary algorithms. Whatever you see in the RAN or in the core network, these are vendor proprietary algorithms, not necessarily data-driven or programmable or configurable or optimal. Now, characterization and optimization of these decisions on the RAN side needs to be guided by more data-driven analytics because of the increasing demand of applications that you're seeing with 5G and beyond. For example, you have these use cases called URLLC, right, which typically requires latencies to be as stringent as 1 millisecond to 4 milliseconds in the user plane. And similarly, when you're looking at applications like 4K video, right, or 8K video, or 360-degree video streaming, now these have very stringent requirements in terms of throughput. So how can you actually meet the performance requirements of such applications that have stringent latency and bandwidth demands? That's perhaps one of the reasons why you need the decisions of your network, both on the RAN side as well as on the core side, to be driven by analytics, to be driven by data-driven analytics. Okay, so that's the role of analytics in 5G, mainly because of the kind of applications that we have for 5G. Now, the characterization and optimization of not just the RAN functions, but also the core network functions are guided by these analytics. Now, end-to-end performance optimization across the RAN, core, and application layers is what will help in giving service guarantees for these applications. And there is a new notion in 5G called network slicing. This is where an operator tries to lease chunks of his resources to enterprise applications. Now, this is a monetization opportunity for the operator. So an operator like AT&T or Verizon or someone like China Mobile would basically be leasing slices to enterprise applications like Netflix, Amazon Prime, or other enterprise applications, so that they would be able to serve those customers with performance guarantees. So when these enterprises are paying for these slices, because the operator is essentially leasing slices to these enterprise applications. So when the enterprises are paying for these slices, they expect certain performance guarantees to be met in return. So that's why you kind of need these analytics-driven approaches for solving optimization problems in your RAN and in your core network. Next slide, please. So we can move on to network slicing in 5G. So the traditional networks are best effort. There are not really performance guarantees. There are not really end-to-end service level agreements. The quality of service is usually implemented using QCI, which is called QoS class index. It's pretty rudimentary. It is not scalable. These are hard-coded service classes that you would see in the standards. For example, QCI 1 all the way to QCI 9. These are hard-coded service classes, and the way these service classes work is that you have a QCI set for a given user session, and those user sessions, basically between the user and the network, are mapped onto dedicated resources in the RAN and in the core network. For example, if you take about 100 resource blocks on the RAN side, some 20 resource blocks will be dedicated for a given user and for a given session. So that is basically the concept of quality of service, which means for that user or for that session or for that class of applications, for example, video applications. So 20 resources out of 100 resource blocks will be dedicated for just video sessions. So no other traffic will be scheduled on those resources. Now, by doing the dedicated assignment of resources for differentiated services, the philosophy is to see whether we'll be able to meet the performance guarantees of these applications. But this was implemented in a pretty rudimentary manner and in a not so scalable manner in LTE systems. Now, the new types of services need to be treated differently, as I said, URLLC, massive IoT, enhanced mobile broadband applications. So that's one of the reasons why we need to guarantee service level agreements across the RAN, core, and application layers, especially when slices of resources are leased by the operator to enterprise applications. So we make use of pretty much a lot of SDN NFV principles to optimize these resources. Open RAN is one such framework that is based on SDN and NFV. Okay, so we can move on to the next slide. Now let us look at an understanding of these slicing requirements. So what you see in the center is the 5G network owned by an operator. You have the RAN, you have the core network, and you have some of the functions of the RAN and the core network listed below. Now, there are three kinds of enterprise applications that you're seeing on the right-hand side, and three different kinds of users that you're seeing on the left-hand side. So the first enterprise application is video streaming, and this is a type of eMBB use case or evolved mobile broadband use case. Enhanced mobile broadband use case. So the requirement of this particular use case is the enterprise wants to make sure that the network can guarantee 1080 pixel of a 360-degree video for each of the subscriber of this streaming session. For example, just think of an eMBB session as Facebook 360. Okay, so Facebook 360, Facebook is trying to get slices from the operator, and Facebook wants to make sure that it's a 360-degree video or even a YouTube 360-degree video streaming session to the user at least has 1080 pixel in terms of video resolution. So this is an example of slicing requirement. Now, similarly, when you look at the second slicing requirement, it is for an autopilot control center, something like Tesla, right? Where you basically have a driverless self-driving car. And the autopilot control center needs to actually send some control to the autonomous vehicle on the road in order to avoid collision, in order to avoid crash for some intelligent transportation services. So this kind of streaming is actually a low latency traffic. So the second application basically wants to guarantee less than or equal to 10 millisecond round trip time with the autopilot and a very high degree of reliability. Not even one packet needs to be getting lost. Not even one packet has to be getting lost. Otherwise, the autonomous vehicle may risk getting crashed or may basically end up facing collision. So the reliability is very important. and the latency is very important. So this this control from the control center to the autonomous vehicle needs to reach with 5 to 10 millisecond round trip time. Now, this is a guaranteed requirement. So that's another example for a slice. And then what you basically have as a last example is health telematics. When you have too many of variables and devices, that even users have, like Fitbit and all of these stuff. And all of these need connectivity with the network. So how can a ubiquitous connectivity be guaranteed when you have so many devices? You can have like all these variables, you can have some some telematic sensors. If all of these need to be connected to the 5G network, how can coverage and capacity be guaranteed to all of these IoT devices? Now, that's basically the third slice. So the operator needs to guarantee these requirements to enterprise applications for the applications to pay these operators and lease slices. So this is the high level understanding of the slicing requirements. We can go to the next slide. So basically what we saw is, we don't have to spend too much of time on this one, but this is the understanding of the 5G RAN architecture. We looked at the CUCP, CUUP, and DU, and we also looked at the loops in which these are present. So what you're basically seeing here is that the CU operations are typically from 10 millisecond to 1 second. That's what we call as loop 2 guarantees. The DU operations are loop 1 granularities, which is 1 to 10 millisecond, and RUs are basically the physical layer for transmission. Now, what we wanted to do is basically look into how these RAN functions work, especially from the context of meeting these slice sessions, and what are some of the bottlenecks that you actually have in the RAN in order to meet these slicing requirements. Next slide, please. So yes, so we can start with this one. So maybe one click. So these are the layers of the RAN protocol stack. So the first thing what you're seeing is there is one user and there is one base station. The same user can subscribe to multiple IP sessions. Okay, like you have N sessions here, and all of these IP sessions are generating IP flows. So one IP session just for YouTube streaming, the other IP session for some file download in the background. The nth IP session is for some email or something along those lines. So you have multiple IP sessions that can be subscribed by the same user. Now there is an entity called SDAP entity. So what this entity does is that it is receiving. So these are entities in the base station that are meant for an individual user. Now these entities, the SDAP entities, are receiving IP flows from the core network, and they are mapping these IP flows to bearers. That's what you're basically seeing in the next PDCP. So the SDAP is getting these IP flows, and these IP flows are mapped to what is called bearers. Now, what is really meant by a bearer? A bearer is a virtual tunnel. It's a virtual connection between the user and the network that has traffic flows. And those traffic flows are treated with quality of service. So when you basically have, when you're basically receiving your oranges, you need to be putting those oranges into baskets, and the baskets basically have a differentiated treatment. I mean, a basket that is colored in red is having a certain differentiated treatment. A basket that is colored in blue is having a certain differentiated treatment, etc. So, the bearers are nothing but these baskets which are treated with certain quality of service. So the flows, the IP flows, are mapped to these bearers, and which is maintained by the PDCP entity. And then you have this RLC entity, which is responsible for segmentation and transmission buffering. And all of these data from the RLC layer. So there is a one-to-one mapping between the RLC and the PDCP layer. And RLC layer is responsible for buffering. So whatever data comes into the RAN, comes into the G node B, they get buffered by the RLC layer. They get buffered into different logical buffers that are maintained in the RLC layer. So there is one buffer per bearer in the RLC layer. And data from these RLC layers get mapped onto the MAC layer. The MAC layer is responsible for scheduling and rate allocation and resource allocation. And then once you basically have data scheduled on frequency time resources, they are transmitted via the cells. Now have in mind that more than one cell can jointly serve a user. A user need not just be connected to one cell, but he can be connected to more than one cell, and more than one cell can jointly serve this user, because that's what we see in LTE advanced in 5G these days, using a notion called carrier aggregation. So this is how the RAN protocol stack works in the user plane. The next slide is about control plane, but I would, in the interest of time, we can skip the control plane and we can just probably, this is about the control plane has a similar, okay, so we can just stay in this slide. So this is good enough. And then the control plane part we will skip when we come to that slide. So what now we need to understand is, how does this RAN protocol stack get mapped to the core network function of the user plane? Okay, so what you're having is, there are 4 slices that you're actually seeing here, which are served by 3 different user plane functions. So user plane function 1 is serving slice 1 and slice 2. And both these slices belong to the same type of traffic, that is, say, an EMBB traffic, right? So both these slices belong to the same type of traffic. So that's why you have one dedicated user plane function for a dedicated type of traffic. Okay. Now, and this user plane is generating 2 PDU sessions that go to 2 SDAP entities within the same G-node B for the same user. And then you have UPF2, which is serving slice 3. This is a URLLC slice, which is basically trying to send data to the SDAP entity and for session 3, for the 3rd session that is being subscribed by the user. And similarly, you have UPFR, which serves slice N, and that is causing a session N for the SDAP entity, which is being served by the user. And there is an SMF, session management function, for each of these UPFs, for each of these slices. Okay, so SMF1 for user plane function 1, SMF2 for user plane function 2, and SMFR for user plane function R. Each of this SMF is responsible for individual slices, EMBP slice, URLLC slice, and massive IoT slice. So this is the connection between the RAN and the core network. This is connecting the dots between the RAN and the core network. Next slide. We can skip this. We don't have to get into too much details, but just one thing to note from this slide is that you have the RRC entity, right, which is responsible for connecting the user to the network. So previously we looked at the user plane layers of the RAN protocol stack. Now this is about the control plane. So there is one RRC entity which basically is responsible for connecting the user to multiple sessions, right from PDU session 1 all the way to PDU session N. And that's what you're basically seeing in the slide. Next slide, please. And this is about the RRC entity trying to talk to the AMF. So AMF is the function in the core network that is responsible for connecting the user to the end-to-end network. So that is this. That is what you're seeing in this slide. And then we can move to the next slide that talks about cardinality of slices and network functions. So basically, just to understand these things in perspective, there are multiple AMFs that can be used to serve different slices subscribed by a given user. One AMF can serve multiple users and also multiple slices. There are multiple UPFs, user plane functions, to serve the traffic corresponding to all of these different slices to a given user. Okay, so one slice can have multiple flows of IP packets, right? And which means each flow of IP packets will have a certain quality of service requirement. Okay, each IP packet flow will have a certain quality of service requirement. This is the last point, is what we saw in terms of the mapping between flows to bearers. So multiple flows can be mapped onto a bearers, and multiple bearers can also. This is just about cardinality, right? So a user can subscribe to multiple slices, multiple flows. The flows can be mapped to bearers. Multiple flows can be mapped to bearers, and multiple bearers can be serving a given user. So this is just the cardinality of slices. Now we'll try to understand what is required to serve these slices, right? So you basically, so what you're seeing here is that so this is how a slice typically works. So you're basically having 3 slices on the right hand side. The SMF UPF, which is used to generate traffic for each of these 3 slices. They connect to the CUCP. They connect to the CUCP and to the CUUP. That's basically what you're seeing in the middle. You have a CUCP and the CUUP. Now these slices send their data to the user plane. So the data transmission will only involve the user plane, which is the CUUP, not the CUCP. CUCP is only for connectivity. Now the data is transmitted to the user plane function, using these virtual data tunnels. That's what so the equivalent of these tunnels in LTE is called the GTP tunnel, the GPRS tunneling protocol user plane function, that is going to connect that typically connects the serving gateway to the E node B. Now, similarly, what you have in 5G is called the NGU tunnel, which is connecting the user plane function to the CUUP, and basically has tunnels meant for each slice of traffic. So you can also have dedicated CUUPs for dedicated slices, just like how you have dedicated user plane function for dedicated slices. You can also have dedicated CUUPs for dedicated slices. And then once the CUUP gets the IP packets from the user plane functions, the CUUP maps the flows of these IP sessions to barriers. That's what you're seeing in the middle between the CUUP and the DU. You basically have three barriers: EMBB, URLLC, and IoT. This is between the CUUP and the DU. And each of these barriers are having multiple flows. And then the DU receives the flows. The DU has the MAC layer that is responsible for scheduling resources for the user. The MAC layer allocates resources based on the quality of service corresponding to the barriers. So the quality of service corresponding to the three different kinds of barriers. So the scheduler can treat the barriers differently. So this is mostly a barrier specific scheduler or a slice specific scheduler. So it's the same resource, it's the same set of frequency time resources, but the scheduler will logically partition the frequency time resources into multiple partitions. And what it does is that it treats each partition differently. Now, this is the high level. So the interest of time, what we could do is we can skip the next few slides and directly move to Open RAN. Now, this is slide number 30. We can perhaps just skip to slide number 30. Yeah, I think we can skip straight to slide 30, and I'll kind of like go to Open RAN. And yeah, I mean, these are most of the RAN details of the RAN protocol stack. This is there in the slide deck for you to review. And all right, so basically, right? Yeah, this is where we can continue. So what you basically had was, when you looked at the RAN layers of the protocol stack, all of these layers basically have certain problems for optimization. For example, which flow needs to be mapped to which barrier? This is the first problem, because the number of flows that you're mapping to barriers is going to determine the buffering that happens in the G node B. So when you have, because each barrier maintains a buffer, so the mapping of flows to barriers is going to determine the buffering within the G node. We know that is one aspect. The other aspect is how are you going to allocate resources to the users? This is the second aspect. And when there is so much segmentation going on, so an IP packet gets segmented into PDU segments in the RAN layer. So the RLC, what it does is that the RLC can segment an IP packet into different segments, and each of the segment is transmitted in a transmission time interval to the user. So all of these things need to be optimized in order to guarantee performance, because all of these are vendor proprietary implementations. They have open problems which are vendor proprietary implementations. So how can you really guarantee this particular requirement is what we will basically see from the Open RAN standpoint. So, as we looked at the two MDAF and NWDAF, and we'll try to see how this connects to the Open RAN. So what is really Open RAN here? So if you can just click onto this one. So basically, right, Open RAN is where I think we can finish the animation, and I'll just explain this from the whole picture. So you have this 5G RAN that you're seeing in the bottom, right? And this 5G RAN talks to interfaces, talks to two components called the non-real-time RIC. If you just click one more time. Yes, that's it. Yeah. So you basically have the RAN talking to two components. One is called the non-real-time RIC at the top, and the other is called the near real-time RIC. So these are the two new components that is introduced by Open RAN architecture. The Open RAN architecture is a different architecture from 3GPP architecture. It does not change the entire architecture of 3GPP. It tries to build on top of 3GPP. So what you see at the bottom is a 3GPP RAN, right? And what you're seeing in the top is Open RAN components called the non-real-time RIC and the near real-time RIC. The traditional RAN tries to talk to the RAN intelligent controller components, both the non-real-time RIC and the near real-time RIC, using open interfaces. So what happens is that through these open interfaces, some key data are exposed from the RAN to the RIC components over these open interfaces of O1 and E2. And the RIC components will basically have certain microservices that will look at the data, do a lot of data-driven analytics and machine learning, and come up with control actions that can be exercised back to the RAN from the RIC. The non-RT RIC, what you're seeing on the left-hand side, is mostly for non-real-time operations. This is mostly for setting policies, objective utility functions, and some guidance information. So, for example, if you want to predict the RAN latency, if you want to predict the RAN throughput, right? So those kind of predictions are done by the non-real-time RIC, and that prediction information is sent to the near real-time RIC using some interfaces. You have these details about these interfaces, which I will not go over, but you basically have these interfaces, and some information such as predicted latency, predicted throughput on an individual user basis are sent from the non-real-time RIC to the near real-time RIC. The near real-time RIC can use that information and can use the information that it gets from the RAN towards coming up with certain optimization decisions, which can be exercised back to the RAN from the RIC over these interfaces, right? So what is the advantage here? So the implementations are no longer vendor proprietary. So using these open interfaces called O1 and E2, the vendor is opening up some crucial insights about the RAN to these open RAN components, and the open RAN components are using that information. They are using that information for coming up with certain optimization solutions, which they can exercise as control actions back to the RAN. Okay? So this is the entire idea about Open RAN, which means you can also have people like Google and Facebook who are not even there in the cellular network vendor business, right? To come up with applications that can be deployed in the RIC. And these applications can basically take some optimization decisions for the underlying RAN. Why Google, Facebook, or Microsoft? Because these people are good with machine learning, right? They basically have a lot of machine learning expertise, which vendor companies or operators don't really have, right? So these companies can basically deploy applications in the RIC, which can use data analytics and machine learning to come up with some optimization decisions for the RAN that can be sent back to the RAN using the E2 and O1 interfaces. So by doing this, you're opening up the RAN for optimization by third party, and you can deploy a lot of analytics in these RIC components, right? More customized analytics. So that's the advantage of Open RAN. Now, with this, right, so we can go to slide 34, and then slide 36 will be the last, conclusion slide. Yeah. So the slide 34 is about, so in step number 1, you're sending some crucial data from the RAN components to the RIC, the non-real-time RIC. The non-real-time RIC is actually using some machine learning out of this, based on this data, mostly offline machine learning that is used to kind of like drive some configuration decisions. So the SMO is basically where the M plane, the management plane sits. So we looked at the management plane functions in the beginning. The SMO is the component, what you're seeing in step number 2, that is the component where the management plane functions sit. And the SMO makes use of the machine learning models built in the non-real-time RIC for configuring the parameters of the underlying RAN. This is what you're seeing in step number 3. And in step number 4, the non-real-time RIC is sending some policies to the near real-time RIC based on the data that it gets in step number 1. And these policies will be used by the near real-time RIC to optimize the RAN. And so the near real-time RIC in step number 6 is also getting some data from the RAN. Now, the difference between what you're seeing in step number 6 and step number 1 is that the data in step number 6 is more of fine-grained data. This is data that goes from the RAN to the near real-time RIC, more of fine-grained data. And whatever you're seeing in step number 1 is more of coarse-grained data that goes from, so what is an example for coarse-grained data? End of session latency, end of session throughput, or spectrum utilization every minute. Now, these are examples of coarse-grained data. And what are examples of fine-grained data? The packet volume every 50 milliseconds. The buffer size of the G node B every 10 milliseconds. This is more fine-grained data. So the fine-grained data goes in step number 6. The near real-time RIC uses this fine-grained data and uses the policies that it receives from the non-real-time RIC in step number 6, comes up with certain reinforcement learning algorithms. You can also have machine learning in the near real-time RIC, but this is going to be more online machine learning. What you can have in the non-real-time RIC can be more offline machine learning, while what you can have in the near real-time RIC is more online or reinforcement learning. And then step number 7 is sending some control actions back to the RAN. So this is how you can leverage Open RAN and analytics using the O-RAN architecture. Because of the new interfaces of O1 and E2 that you are introducing in the cellular radio access network, and because of applications that come from third parties, not just from Nokia or Ericsson or Huawei or vendor companies, Samsung or even Mavenir for that matter. You can also come up with microservices from third parties and deploy them in the non-real-time RIC and near real-time RIC for customized solutions for the RAN. Okay, with this, we'll go to the last slide, which is slide number 36, and then we can wind up the presentation. Yeah. Yeah, these are just some insights about the data. So finally, right, how does the how does O-RAN figure in end-to-end analytics? So basically, what you do in the near real-time RIC and non-real-time RIC is that you have the analytics function. So the non-real-time RIC is deployed, is what you're seeing at the top. It is deployed within the SMO. The SMO has all of the M-plane functions. So whatever you saw in management plane, right, O&M management plane, all of that is built within this component called the service management and orchestration framework, which also deploys the non-real-time RIC. Okay, so the data from the RAN goes to the SMO, which hosts the non-real-time RIC over O1 interface. And look at this component MDAF, which is the component for analytics, M-plane analytics, management plane analytics. The MDAF sits in the SMO. It looks at the O1 data from the RAN, and it comes up with some interesting analytics, such as, for example, predicting the throughput, predicting the latency, predicting the packet loss. This is what the MDAF within the SMO does. Similarly, you have the near real-time RIC at the bottom, right? This gets E2 data from the RAN, more fine-grained E2 data from the RAN. There is also an analytics function in the near real-time RIC. Both the analytics functions, both the MDAF inside the SMO and the analytics function inside the near real-time RIC are predominantly used to compute all these prediction insights or all these KPIs, key performance indicators, etc. And this can be sent to the core network using these service-based interfaces that you're basically seeing in green. So that's how the core network also has an analytics function called NWDAF, Network Data Analytics Function. It receives all of this data from the SMO, from the non-real-time RIC and from the near real-time RIC. And the core network analytics function, which is the NWDAF, can use this data to optimize the operations of the AMF, SMF, and UPF. Previously, right, AMF, SMF, UPF interact with the RAN, but that interaction is based on protocol and standards. It is not based on data and intelligence. The MME talks to the E node B. This S gateway talks to the E node B. The AMF talks to the CUCP. The UPF talks to the CUUP. But all of this interaction is based on protocol and standards. But now you see how the interaction is based on data and analytics. So in addition to protocol and standards connecting the core network and the RAN, you also have data and analytics that is driving some crucial decisions of the core network. Now, this NWDAF will get the data from the MDAF and the analytics to optimize the functions of the AMF, SMF, and UPF. Okay, so this is how we're connecting the dots. And then one last slide is on the with this we can end the presentation. So yes, you can finish the animation. So this is one example of how things work in place. So the RIC, right? It can be the non-real-time RIC. It can be the near real-time RIC. It can talk to O1, it can talk to the RAN using O1, E2. It has some interesting predictions of latency, throughput, etc. Now this is sent to a cloud platform that you can deploy in the edge, And that cloud platform can have a lot of analytics, like NWDAF kind of analytics. These analytics is mainly for the core and applications. So the cloud platform that you're seeing here on the top right, this will receive some interesting insights from the RAN and will translate those insights into some application layer analytics. For example, can you use RAN throughput to determine what should be your optimal video bitrate? Okay, so if the RAN throughput is good, then your resolution of the video can also be high. Can you use your RAN latency towards determining your IP packet sizes? If your RAN latency is very high, can you reduce your IP packet size? Instead of having a 1500 byte IP packet or even larger, which will result in segmentation in the RAN, can you reduce your IP packet size so that the IP packet size is not going to incur latency? These are some decisions that you can do in the cloud, and those can be sent to the application server using these cloud-based APIs, edge APIs. That's what you're seeing in terms of IP packet size or video bitrate guidance between the blue component, which is the edge, and the application server. And the application server will then be able to reflect these insights about the RAN, about the core, and will get some intelligent guidance or recommendation from the edge towards optimizing some of its functionalities, like choosing a proper resolution, choosing a proper bitrate, trying to change the IP packet size or MSS size. These are some of the decisions that can be taken in the application server. So this is how the RIC will help in end-to-end analytics. And then we can go to the conclusion, and the next slide is conclusion. I think we can leave this one. This is just some results from our research paper, but finally, right, so we looked at, so in conclusion, we looked at these architecture analytics, we looked at network slicing, we looked at some of the challenges, and then we looked at Open RAN analytics, and then we looked at how this can be used for end-to-end analytics and optimization. That concludes this talk.